everybody. I'm very happy to have so many people in the at this hour to join us for our little webinar. Um, I think we're going to wait for a couple for 1 or 2 minutes. In the meanwhile, um, if you like, you can say hello and tell us from where you are joining, and you can take the little poll that we just put up. That allows us to understand a little bit more where you're coming from and what you're doing already, while we're waiting for a couple of the latecomers. Um, but yeah, so say hello and tell us where you're from. So I'm in lovely Berlin. Our weather is today very changeable, very moody. We had already hail, we had sun, we had rain, we had a thunderstorm. So I was like, that's that was not very nice. So I'm pretty happy to join you all and hear where you are from, so that I can envision myself being in Brazil or in Australia. Um, all right, Ontario, Canada. That is Kenya, East Africa. Nice. Yeah, I'm going to. Well, that's kind of like Kenya is far away from South Africa, but I'm flying out to South Africa on Sunday, um, to visit some mines there. Nice. All right, from Germany, Peru, Tucson, South Africa, really nice. All right, Johannesburg, yeah. I'm so then I think it's time that we say hello to Max, who's going to present to us accessing mineralogy. Um, and then in the end, I'm going to tell you how kind of like what could be the next steps. But for now, Maxwell, take it away.
Great, thank you, Sebastian. Yeah, let's get started. So today I will talk a little bit about general aspects of quantification from X-ray diffraction, and particularly for mining and mineralogy. I'll tell you about our rapid access and high energy setup, and about the benefits of high energy X-ray diffraction for mineral quantification. And then I'll talk about a few examples as well. So
Max, real quick, I forgot the most important part. We are going to have a question and answer session and Q&A session in the end. So whenever you have a question, just shoot it out. If we see it, and can answer it right away, Max will do that. Otherwise, we will have an extended Q&A session in the end where we go through everything and we answer everything from anybody. Thank you. Sorry.
No. Oh, good. Thank you. Yeah, so, in talking about how can X-ray diffraction be useful at scale for mineralogy, so I wanted to kind of show an example map of, kind of a mine for gold. And so if we imagine we have this swath of land and we haven't determined anything from it yet, and we take our core samples, we start to look into the details of all these different zones. And the fantastic thing about X-ray diffraction is it can in detail tell you what phases are present in all of your different samples, and also quantify the relative or absolute amounts of phases in those samples, so that you can take that information and map it back to your mine and do your zonation and build your resource models and really understand everything that you're working with. And of course, it goes further than that. You can, take these techniques on further to processing stages and production stages for quality assurance and quality control, and to actually make sure that your ore feeds are kind of the caliber that you expect, to understand changes due to moisture. Certain types of clays take up water from the environment, and potentially other interesting details, other kind of indicators. And we've also talked to a lot of people who are kind of sitting on tailings, and maybe interesting to go back and look at other kind of interesting minerals that are present in there to do something with those kind of materials that are sitting around as well. So X-ray diffraction is really excellent because it can give you all of this information to really map out what's in there and how that relates to kind of zonation in your resource models, indicator compounds, and how these things are changing as you change location. So X-ray diffraction, from a kind of very simple perspective, is really easy to understand because essentially different minerals have typically different crystal structures, and those crystal structures give a different fingerprint in X-ray diffraction. So the crystal structure gives a set of peaks in the X-ray diffraction signal that are dependent upon basically the repeat spacings in the crystal lattice and the atomic positions. And so for different crystal structures, you have completely different sets of peaks, different relative intensities. And even in cases where you have similar crystal structures with slightly different compositions, because of expansion or contraction or changes in the density of the material, you can get shifts in those peaks. So that allows you, in many cases, not all cases, to also discern different compositions as well. So this is an example of just actually some kind of metal and metal oxide nanoparticles. So it's not interesting from a mineral perspective, but I wanted to demonstrate the fact that we can identify crystalline peaks, which show up as sharp peaks in your pattern. But in some cases, when you have sufficient information or you know what you're looking for, you can also find disordered or nanoparticulate phases. And so you can also discern these signals. And so you can see in this case, the peaks are much broader in the black curve than in the green. And this is because the crystallite sizes are very much smaller than in the green curve. Okay. And actually, even with synchrotron diffraction, which I'll talk about in a bit, you get signals that are so good that sometimes you can also observe even sort of surface layer effects and things like that. So in this case, this is actually just a layer that's in nickel metal enriched with platinum, is this orange curve. So you can see this is very small crystallite sizes. And then once you've detected all of these things, you've identified all of the fingerprints from these component patterns, you can actually take these models and quantify the amounts of these materials in your sample to get back a very clear picture of everything that's in there and how much. Okay, and so how do we do this? How is it typically done? How it's typically done is with laboratory diffractometers, or in some cases, people have sort of more portable devices that are used in the field. And these lab sources work on essentially metal anode tubes. So typical is copper or cobalt, and for reasons that I'll get into a bit later, sometimes molybdenum or silver or other metals. So these kind of anode tubes can generate about 10 to the 8 photons per second in terms of X-ray flux. So this is pretty good, but this hasn't changed with the current technology from also about 40 or 50 years. So this technology is basically working the same way that it has been. And the measurement times to get a very good pattern for quantitative analysis with a device like that is typically a few hours. And I can say in my previous research position, we were often kind of measuring samples overnight for 8 to 10 hours when we wanted to get a really good pattern to publish in a paper, for instance. You can do very quick measurements in some cases, but the ability to really quantify things or the ability to detect trace levels of components is very difficult in those cases. And typically you can measure a few samples per day if you want to collect that kind of quality. We work at facilities called synchrotrons, which are basically large particle accelerators, and they accelerate electrons around a big ring. And this ring is a giant instrument that's the size of a building, essentially the size of a big stadium. And these electrons orbit the ring close to the speed of light. And as they change their path, they actually give off very high fluxes of X-rays. So at the beam line that we work at, where these X-rays are kind of directed, we collect something like 10 to the 14 photons per second. So with this kind of flux, you can do measurements in a few seconds of the very high quality that you would need hours to collect with a laboratory device. And we can collect thousands of measurements in a day. So that allows us to sort of bulk up the statistics on what you can do in terms of observations. And the other important thing, and I know I'm kind of jumping all around this table here, is that we're working at much higher energies than what you have accessible with laboratory sources. So actually 75 keV, kilo electron volts. And so this allows us to kind of take advantage of a lot of benefits of that in terms of how we do the measurements and in terms of the quality of the data. And so I'll talk a little bit about that in a bit. So the synchrotron high energy setup. What are the key kind of details of this setup? We use a monochromatic beam. So that means we have very fine energy bandpass, single energy essentially. So we don't have to deal with the effects of having diffraction from multiple energies in our data. We work at very high energies, again, compared to laboratory diffraction systems. So with these kind of systems in general, with synchrotron powder diffraction, oftentimes 60 keV or more if you want highly penetrating X-rays. So we work at 75 keV, and this allows us to significantly minimize absorption from the sample. As I said, the X-ray flux is extremely high, so that allows for very quick measurements. And we also use large area detectors so that we can collect a wider spread of the X-ray diffraction signal rather than using point detectors or position-sensitive detectors that typically only collect a very small part of the diffracted signal. And finally, we use a lot of instrumentation in this beam line to actually collimate the beam and reduce the background. So to get rid of any kind of artifacts from instrumentation upstream, and also to decrease air scattering. In addition to that, we also measure the experimental background and subtract it from the system. So there's a lot of kind of data processing that gets coupled into this. So because we use large area detectors, we do a lot of corrections for the geometry of the detector. We correct for absorption into the detector pixels, polarization of the beam, oblique incidence. We also correct for offset errors. So for instance, with laboratory systems, you sometimes have a height error because it's very difficult to control the exact height of the sample on your sample holders. In this case, we have a very precise positioning of the sample, and we can correct for any detector-based offset errors, which mostly come from parallax, which is the effect of having a flat detector. And we do this using calibration standards from NIST. And finally, as I said, we subtract the experimental background, and we also correct for the instrumental profile. So the amount of broadening that comes from the measurement apparatus itself rather than the sample. So from this setup, we can get very high resolution data. And if you compare sort of a typical diffraction peak from a highly crystalline material from our setup to typical lab devices, you can see that the line profile is a lot thinner, but it's also much more symmetric than a lot of laboratory devices. So part of the reason for that is, and you see in this signal from molybdenum K alpha, there's this very significant asymmetric broadening towards the lower Q or lower angle part of the signal. And this comes from what's called axial divergence. So with these systems, you typically only have a position-sensitive detector that just measures part of the diffracted signal, which is essentially a ring. And as it sort of passes through that ring, it measures the edges for a longer period of time, and then finally passes through the outer part of the ring and essentially is not measuring anything anymore very quickly. So that's what causes this tailing towards lower angles. So, I mean, this can be modeled and corrected for, but it generally reduces your ability to resolve sort of shoulder peaks or peaks that are very close together underneath that curve. And the other thing is this very symmetrical and sharp profile makes it much easier to model the data. And so we can get very good refinements from any kind of structure phases from, for instance, Rietveld refinement. Another thing is that because we have very high flux X-rays, we can get a very good signal to noise. And also coupled to that, having a monochromatic wavelength allows us to reduce significant artifacts from other wavelengths in the measurement. So on the left-hand side here, you see a comparison of a copper K-alpha system. So it has essentially a nickel K-beta filter, but you still have copper K-alpha 1 and 2 signals, which are the two significant emissions from a copper K-alpha system. And so every peak actually gives a doublet. So you have to model both of those. And because you also have essentially a wider spectrum of white radiation underneath that, you also get a larger contribution to the baseline from white radiation scattering. As compared to our system, you don't have this doublet and you don't have all of this extra scattering from kind of non-monochromatic wavelengths. In terms of noise, also the detection limits, so the ability to resolve phases at much lower weight percentages is possible because essentially we can reduce most of the noise from the statistics of the measurement itself, and rather the remaining noise in our measurement comes mostly from the detector itself. So for typical lab systems with multi-phase mixtures, oftentimes you can get detection limits down to 1 weight percent, maybe 0.1 weight percent if you have really, really good system and really, really long measurements. For us, in just a few seconds, we can get detection limits oftentimes down to sub 0.1 weight percent, in some cases down to 0.01 weight percent. And also we have a very reproducible instrumental profile. So one of the tricky things working with these facilities typically is done through general user programs where people apply or buy beam time to come. But because these beamline stations are very flexible to do lots of different kinds of measurements, oftentimes you kind of get the whole system in a slightly different state every time you use it. So sometimes you use slightly different wavelengths. Sometimes the detector needs to be in a slightly different position. Sometimes different devices have been changed in between. So we are generally dealing with hardware upgrades, but we try to mitigate that by making proper corrections in the data processing to account and normalize for all of those. But we also have a very systematic experimental setup that we run basically every 2 weeks. And this is very highly controlled in terms of all the motor positions, in terms of the wavelengths used. And so we get a very reproducible signal for our reference materials and a very consistent instrumental profile. So this means that it's very easy to compare data across different beam times directly, as opposed to other cases where you might have to do a lot of extra sort of data massaging to be able to directly compare the data. So now I want to talk a little bit about the high energy aspect. So high energy is great because this actually makes the X-rays much more penetrating of any samples that we put into the beam. So it significantly decreases the probability of absorption. So as an example, and I'll show how this works for typical setups in the lab versus ours, I take zirconium silicate here. And what I've calculated is the transmission of each of the elements as a function of X-ray energy. And basically the way that it works is, as you go higher in energy, your transmission should go up, so absorption goes down. So in this case, we have mu, which is the mass attenuate, or actually the linear attenuation coefficient of the sample, which is 234 inverse centimeters. And if we use copper K alpha radiation, which is the typical radiation for most lab systems, which is an energy of about 8 keV, then the attenuation length of this zirconium silicate sample is about 42.6 microns. So that's a very thin bit of material that is all you need to essentially stop all of the X-rays from passing through. So if we're working with a Bragg-Brentano system, which is a reflection geometry, your X-rays are incoming to the surface of your flat sample and then outgoing back in the other direction. And so a typical flat plate sample might be prepared with a thickness of about 0.5 to 2 millimeters of powder. And actually your X-rays are only diffracting significantly from a very thin surface of this. So if your material, for instance, is not very homogeneously mixed, if you have some much larger crystallites or particles in your sample, then you're significantly biasing the material that you're actually probing in your sample. Okay, so this is not very, very ideal. If we go to a Debye-Shearer geometry, which is a typically capillary transmission geometry, you have a similar effect. So same material, same energy, attenuation length is the same. Working with capillaries, you typically use inner diameter of about 0.1 to 0.7 millimeters with either a glass, borosilicate, or quartz capillary. You can't typically go much smaller than that because then they get almost impossible to load the powders into the capillary. And if you go much bigger than that, I mean, you can already see here that I'm essentially blocking all of my X-rays with this particular sample in this case. So typically you have to use then a filler material, which decreases the overall mass attenuation of the sample. But that means you have, again, far less sample in the beam. With 75 keV for our setup, now your linear attenuation coefficient goes to 2.75 and attenuation length is 3.6 millimeters. So even working with a 1 millimeter sample, now we can pass through much more, a much wider thickness of our sample and probe through many more different particle orientations. And we don't have to deal with this issue of significant absorption artifacts or quenching of our signal. We also get reduced microabsorption, and this is particularly important for phase quantification. So if you have a mixture of different minerals in your sample, different minerals will have different mass attenuation coefficients. And that basically depends on the mass of the unit cell and the volume of the unit cell and the weight percent of that material in your sample. And it's also affected by particle sizes. So if you have very big particle sizes, it gets even worse. That part's a bit hard to predict. But generally, you ideally want particles or crystallite sizes in the range of about 1 to 5 microns. For high energies, so I should say, so the whole point is that actually some particles that are very big or have much larger mass attenuation coefficients will essentially absorb the most of the X-rays, and that kind of shadows getting some diffraction from the lighter phases or the smaller particles. And so this can bias significantly your estimations of the relative fractions of those components. So high energy does two good things. One is it reduces the attenuation coefficient for all phases, high energy, less absorption. But the other thing that it does is it can, although not always perfectly, reduce the differences in the mass attenuation coefficients. So that's something to consider. Is like, even if you go up in energy and all your mass attenuation coefficients go down, there can still be some differentials between them, and you can still get microabsorption effects from that. However, the amount of absorption from all those phases is a much lower percentage, and so this is having a lower significance, and also the differences can kind of even out a little bit at higher energies. So that also can reduce this effect, which is very good. There's another effect related to the energy, which is the effects of fluorescence from the sample. So fluorescence happens when your working energy is slightly higher than the energy required for the X-ray to knock an electron out of the atoms in your sample. So you have certain elements that are sort of problem elements depending on the characteristic energies that you're using. So unfortunately, while copper K alpha is typically the most commonly used in the lab, this is actually the most problematic for pretty important elements for kind of a lot of minerals, which is titanium to cobalt, and particularly for manganese, iron, and cobalt. And so in those cases, oftentimes people will then change their system to a cobalt radiation, which is slightly lower energy, and then you don't have problems from iron and cobalt. Alternatively, you can go to higher energy, which is like molybdenum or silver K alpha radiation. In those cases, you have other elements that are slightly below the working energy that cause the most fluorescence, that are maybe, you know, kind of less bad. With 75 keV, then we significantly move up the elements that fluoresce significantly into the kind of higher side of the lanthanide series, and then hafnium up to osmium. So at 75 keV, you're sort of right between the energies where you have just enough energy to knock electrons out of osmium, but not enough for iridium. So iridium doesn't cause any significant fluorescence. But the good thing about this is, in addition to that, like, we have a very high flux of X-rays. And so one of the issues that you run into with getting kind of worse quality data from these lab systems is that the fluorescence signal has its own noise associated with it, and that noise never gets better as you collect more statistics. So that kind of reduces your overall signal to noise. But in our case, the flux is so high that you can still collect a good signal from the part of the sample that you care about. And so as an example, I take pure tungsten metal here. So you can see tungsten is kind of right in the middle of the ones that are closest to the problem area. And actually, while we do have a sort of an elevated baseline of the sample, so all of your fluorescence scattering is underneath that baseline, it actually doesn't really affect the quality of the diffraction signal too much. So this has to be accounted for in phase estimations, but it doesn't significantly reduce the detection levels, basically, for having this kind of system, which is good. Another thing that I mentioned is that we use the area detectors. And this is really beneficial because it allows you to collect a little bit more information about the sample, potentially, if it's not an ideal sample. So when you work in the lab and you have a point detector or position sensitive detector, basically you're just measuring on a point. And I think you can't see my mouse, but if you look at the image on the far left-hand side, there's a little black circle. And that little black circle is essentially the direction of where the incident X-ray beam is pointing to the detector. And as you go out radially from that, going to sort of the lower left-hand side, you have these rings. And these are Debye-Shearer rings that are the diffraction rings from the different lattice spacings in the phases of your sample. And so if you have a point detector, you're only kind of collecting one slice of that. And if you have a PSD, a position-sensitive detector, you're collecting a sort of a slice with a little bit of thickness to it. So you only collect sort of like a line scan in the radial direction. But with the area detector, you collect a much larger arc of these rings, and that allows you to look at this image and actually determine the quality of those rings. For an ideal powder, meaning that you sample all of the crystallites kind of in all orientations, then this should be azimuthally homogeneous or symmetric. And then having the 2D image doesn't add any information. So we integrate it all down into a 1D pattern. However, if you have a non-ideal sample, for instance, if you have preferred orientation where the crystallites are aligning in a certain direction, you can see streaks in your rings. Or if you have a coarse powder, meaning that you have very large crystallites and you're sort of only sampling a minimal distribution of particle orientations. So you start to get sort of spots in your data. This is more difficult to detect when you don't have these images. So this allows us to get feedback in terms of the quality of the data holistically, and also to optimize sample processing procedures depending on whether these instances can occur. And so we've developed kind of data quality metrics to measure that, and we measure these and provide these in our web application for data return. So on the right-hand side, you can see a case where the rings are very faint, but actually they're very spotty. So the summed error and sort of the azimuthal homogeneity of the rings is very low. And so that allows us to go back and remeasure samples when they're not very well prepared, let's say. So just a further point on this preferred orientation, if you look on the left-hand side, I have two images here. So one has sort of more spherical looking particles, and in an ideal powder, you want to measure all of your different crystallites and particles statistically in all directions so that you collect sort of a spherical average of your diffraction signal in all directions. But what can happen sometimes if you have needle-like or plate-like morphologies is that these particles can start to stack up in a way where they're all sort of aligned along the same direction. And if you have this, which is called preferred orientation, it can significantly impact the relative intensities of the peaks in your signal. So if you know what the structure is, you can correct for that in a refinement. However, sometimes this can cause issues with identification, and it can also decrease the accuracy of quantitative analysis as well. So with Bragg-Brentano or Debye-Shearer geometries, you can exacerbate this alignment effect because, for instance, if you have a flat sample holder and you're putting your powder down onto the sample, they tend to align along this flat plate. And similarly, if you have very thin capillaries and needle-like morphologies, for instance, then the needles tend to align along the capillary. And spinning your capillary or spinning your plate doesn't really improve the data in these cases, because as you spin it, you're still sampling the particles from the same direction. In our case, we use a slightly different flat plate transmission geometry, and we have these sample holders with wells that are cylindrical, about 1 millimeter in thickness and 2.5 millimeters in diameter. So the good thing is the geometry itself having a much thicker volume for the sample to collect in and the beam to pass through fully allows you to reduce the chance that you're significantly biasing your results by alignment over just a kind of small, thin area. But the other thing is that we also fluidize the powders in these wells as well. So during the measurement, the sample holders are vibrated to actually move the powder around in the well, and the whole sample holder is actually translated back and forth in the beam so that your X-ray beam scans along different regions in the sample. We're actually developing a further kind of spinning device to further kind of randomize the samples in the beam as well. And so hopefully that will be ready towards the end of the year. So a further point to crystallite size reduction is really important to get good data. And so typically you really want crystallite sizes in the 1 to 5 micron range to avoid these more significant microabsorption or particle orientation biasing effects. So typically you grind your powders down and micronize them to do that. And another thing to keep in mind is that the particle size and the crystallite size are two slightly different things. So particle size is really the kind of aggregate clusters of material in your sample. They could be a single crystal, but they could also be a clump of many smaller crystals. So in that case, it's no problem, because what the X-rays see is actually the coherent scattering domains, which is the length over which the structure scatters the X-rays coherently, which can be the crystallite size, but can be typically a bit less if there's sort of defects in the material, which is certainly the case for many natural materials. So you can sieve these particles out, sort of grind them out selectively and add them back in as an example. And there's different ways to do size reduction, from hand grinding to the standard method, which is macrone milling, which is essentially roller mills that are low energy, up to more kind of aggressive shaker and planetary mills. And these really depend on the type of material that you're working with. For very hard minerals, hand grinding and sometimes even micron milling is not sufficient to really grind them down very well. Whereas if you overuse shaker or planetary mills, you can sometimes have a higher chance that you degrade the sample either through significant crystallite size reduction, strain generation, or potentially amorphization. So you sort of have to tailor the size reduction techniques to the particular mineral mixtures that you're working with to make sure you get optimal results. So this is something that's often tested to find the best results, although there are sort of generally recommended starting places for certain types of materials. So now I'll just quickly go through some examples. The primary, or let's say most common method that we use to analyze the X-ray powder diffraction patterns is Rietveld refinement. And through this, we're essentially taking a model of the atomic structure of the material and simulating a diffraction pattern from that to match against the experiment. And then what we can do is refine different parameters of that structure model to understand a lot of details of the material. So this includes the lattice spacings and the contents, which is essentially the crystal structure and the density of the material, crystal symmetry, which is responsible for not only the structure, but also a lot of the properties of the material. And then also microstructural information like crystallite size or size distributions, even the morphology in some cases. So if it's sort of elongated or platy morphologies, or rather more isotropic. And we can also measure macro and micro strain as well. Furthermore, you can also kind of indirectly, or in some cases directly, get information about amorphous content. So amorphous materials don't produce sharp diffraction peaks. They produce a broad, diffuse halo of scattering that sort of sits in between and underneath these peaks. And so this comes from amorphous content, but it can also be affected by nanoparticles, and it can also be affected by disorder in certain phases. And so that can be quantified as well. So I give an example here, which is not a mineral material per se, but just to also kind of give an example of the idea of what X-ray diffraction can bring to processing. And this is actually a case of pre-cathode active materials for battery development. And these are layered double hydroxide. So they're nickel, cobalt, aluminum, oxide, hydroxide, layered materials that are used for generating cathodes. And X-ray diffraction is extremely useful in characterizing these systems during processing and production, because it can give very detailed observables that help to predict the performance of the material and also how best to optimize the processing. So one example is the lateral extent of the layers. So sort of if you look on the right-hand side, on the bottom, you see the layers kind of going horizontally across the page and how they stack together. And the dimensions of that lateral crystallite are really important to predicting the cycle stability of the material. And so by measuring that, you can already predict whether a product is going to perform well or not. And on the process optimization side, there's precursor disorder. So this comes from both the stacking patterns of these layers. So they can have different kinds of stacking patterns that can intermix and cause stacking faults. And you can also get to what's called interstratification, where you have different kinds of guest molecules that come between the layers and change the layer spacing. And you can quantify these properties, again, from X-ray diffraction. And this helps to predict the ideal temperatures to actually calcine the materials. So the main application that we see with mineral analysis is phase identification and quantification. And in that sense, we can use these data to search for candidates of structure phases that are present in the material by reference pattern matching, which I kind of showed in the beginning. We can use preliminary refinements to validate the presence of those phases, and then complement that, generally in an ideal case, with chemical analysis or other information that can help to rule out cases where there might be similarities in candidates that can be difficult to distinguish. And then we can quantify all of those components as well. So from a detection perspective, again, we have fingerprints of certain peak positions and relative peak intensities that come from different phases. So in this case, we have titanium dioxide, rutile, and anatase, and I've sort of highlighted them in different colors in this pattern. So you can very clearly see the presence of these two components in this mixture and identify them from those peak positions. And so we've actually developed our own phase identification tool, which we have in our platform online. And in using this, we use currently the crystallographic open database, but also in our own analysis projects for customers and for people that we work with, we also use the ICDD, which is the International Center for Diffraction Data database. And this has actually many, many thousands of reference structures that we can use to match and identify these peaks. So in this case, again, I just showed this example of rutile and anatase, which is easily pulled by kind of isolating the peak positions and intensities. And this is actually free for people to sign up and try out if they're curious. And it can also be used with laboratory source data. And then you can compare it to data measured with us as well. So phase quantification, once you've actually identified, or at least done a preliminary identification, then you actually have to validate these phases by fitting to the pattern. And for many mineral samples, you can have well upwards of 20 or 30 phases present in a single sample. And so the example that I show here is actually from the Reynolds Cup, which is a competition for quantifying clay minerals. And there's a lot of different things mixed together here. So this is a sample meant to represent old red sandstone. And we essentially, in this case, have the actual weight percentages that were all mixed together, both of non-clay and clay components, and what we determined from the multi-phase Rietveld refinement. So you can see when you do an accurate job of identifying the phases, then the quantifications are highly accurate, typically well within a couple of percent or less in terms of the delta between determined and actual. So it's a very accurate technique when the phase identification is done properly. And you can actually see how complicated this gets when you're having so many phases. The different components are significantly overlapping for different phases present in different angular ranges in the material. And so it's a bit of an effort process to do the identification, but with very good quality data, it really makes this job a lot easier. It really gets rid of a lot of the things that kind of make this tricky. So when doing this, there's different styles of refinements and sample preparation that you can use. So there's typically what's called semi-quantitative analysis and quantitative analysis. Semi-quantitative analysis, you can actually directly use the relative scalings of all of these different phase contributions in your sample to estimate the phase fractions in your material. So if you don't have a significant amount of amorphous material present, a few percent or less, then these will already directly be representative of the phase concentrations or mineral concentrations in your sample. In cases where you have a large amount of amorphous material present, then there are different methods to estimate the amorphous content as well. So we typically use a method called the internal calibration method, where we add a known weight percent of a reference material into the sample. So in this case, for instance, a bit of titanium dioxide. And from that, we can renormalize all of the values of the identified phases and then subtract that from 100% to get back the amount of amorphous phase. There are other methods that you can use to do that with varying accuracies in different cases. So there's also external calibration methods. There's sort of methods where you use kind of other measured reference materials to add directly into the refinement. And yeah, it depends on sort of what kind of system you're working with. But the internal calibration method is generally what we use and is working very well in most cases. So as an example of semi-quantitative analysis, this is an example of a copper porphyry study where we had a kind of large swath of different samples from different regions in the mine. And particularly interesting, again, in the very first example in the presentation for zonation, but also for deportment to understand where the valuable elements are located in the minerals. And so these are kind of an example of the different patterns that you might see in the quality of fitting that you get from the phase mixtures. And again, we generate very detailed tables for all of these different samples. So non-clay and clay components, weight fractions, and you can also see here the reproducibility. So in many cases, we have the application to measure multiple subsamples of a certain material because we can do the measurements so fast. So you can actually do statistics from a measurement level on kind of the reproducibility of these values for a given batch of sample. And you can do lots of interesting things from this. And so I won't go too much into detail into the specific applications, but you can classify your minerals per sample to look for, where it's likely to be coming from different regions. You can look at mineral abundance. So what types of things are showing up most often in your samples and what are relatively rare. And you can do phase correlations, for instance, to say what types of minerals are typically showing up with other kind of specific minerals. So which ones are highly correlated together and which ones are not. And so with that, I will let Sebastian take back over and talk about how to work with us.
Yeah. So how to get started? If you like to get this kind of precision, and on kind of like some kind of scale, you can just, the easiest part is you can kind of like call a book a call with Max and myself. What we would do is we would define kind of like see what your goals are, what do you actually want to achieve, what kind of existing knowledge do you have, and what you can share with us, so the precision of the final analysis becomes as good as it gets. We want to define the timeline and configure the budget for the pilot. The next then would be that you send us 50 samples, and we would need something between, it depends on the first pilot. We would want to have something between 5 and 10 grams. Don't think boulders, and don't think kind of like micrograms yet, or milligrams. Yeah, 3 orders of magnitudes. Milligrams. So then, with the first pilot, we establish the logistics, we validate our sample preparation. That's what Max talked about. Kind of like how fine do we have to mill it? Do we have to mill it at all? We want to see how much amorphous versus crystalline is there, and then we want to build our mineralogical model. And then you can decide to go for full project. So that means anything between 500 and 50,000 samples. And then kind of like we can do multiple batches if needed, and you would take that and do what you want with the data. So this is how you would work with us to get started. And the timelines for those are, so we are every 2 weeks at the synchrotron. That is one of the kind of, I would say, that's often the critical path for smaller projects. And then if we need to do a extended amount of sample prep for larger batches, then that could play into the timeline. But that's happy to talk to you about this in the first call. So if you have a project, happy to book a call next or in the next 2 weeks, and see if this is right for you and your projects. And now I would say, kind of like we get into the questions. First questions are, there's the first questions here, and the first one that is from Jemima. I'm sorry, I'm terrible with names. Jemima from Kenya. Is it advisable to, I would say, grind samples with needles, like needle-like minerals, like cellulite samples? So how fine would you grind those? to avoid the preferred orientation, Max?
Yeah, so as I said, I mean, typically in an ideal case, you would have isotropic particles in the 1 to 5 micron range. Of course, that's practically not possible in a lot of cases. You also had to be sort of sensitive to, your particular minerals have different sensitivities to mechanical agitation. So if you have something that's very sensitive to being mechanically ground up, that you transform the material or generate a lot of defects in the material, that's something that also has to be considered as well. Generally, yeah, if you have very highly anisotropic particles, should try to grind them down so that you can minimize the issues that come from preferred orientation, which will certainly happen if you have particles like that, because then you're just have a much higher probability to sample the particles only in certain directions. But you have to then, implement a size reduction mechanism that sort of maintains the structure of the material as well as possible.
Brilliant. Adam is asking, what materials are good as internal standards for quantification with titanium dioxide that is actually expected to be in the sample?
Yeah, that's a really good question. So, I mean, generally, you want a material that has a very good crystallinity. So again, typically in the 1 to 5 micron range, you don't actually want it to be much smaller crystallite sizes than that, because then if you have kind of, a few hundred nanometers or less, then the size will actually start to broaden the peaks from your reference material. So you want the peaks from your reference material to be really, really sharp. And you want the material also to have a similar mass absorption coefficient to your sample. So for instance, if you had a sample that was really heavy elements present, then you might want to use something more like lanthanum hexaboride or something like that. So that's one aspect: simple structure, highly crystalline, kind of isotropic if possible, and easy to model. But you also want to sort of calibrate your standards very well. So what we start with typically is very well characterized samples from NIST, so the National Institute of Standards and Technology, and they make standard diffraction materials, actually SRM, so standard reference materials for different applications. So typical materials are silicon and lanthanum hexaboride for sort of profile refinements. And for quantitative analysis, the typical samples are zinc oxide corundum, titanium dioxide, cerium dioxide, titanium dioxide. But there are other things that you could use as well. You could use, kind of crystal baylite or quartz if you don't have that in your sample. The important thing otherwise is, your reference material shouldn't be in the sample to start. That could cause problems, obviously. And the other thing is, you could take other materials and then you can calibrate them against the NIST standards. So for the NIST standards, they do actually have values for the amount of amorphous content, which obviously can come from surface relaxation on the crystallites, regardless of the size, but can also come from defects that are inevitably present in the material. So you can mix one of those NIST standards with your new material to sort of calibrate the amount of amorphous content in that, and then you can use some other material as a calibration standard as well. So those are pretty much the main things to keep in mind.
Okay. So Mike is asking, for the refinement stage, is that process automated, or is each sample independently reviewed prior to release?
Yeah, so there's different strategies for this depending on the scale of the number of samples to analyze. So for like trial, small scale starting analyses, we really want to make sure that we understand what the minerals potentially in your system are. So we do like an isolated analysis of each data set, really do the best possible job that we can to identify everything in there and quantify it, and then check to make sure everything makes sure mineralogically sense, and also the kind of results of the refinement make sense. For larger campaigns where you're maybe sampling, hundreds or thousands of samples from similar regions in the material, then there are different strategies where you basically first want to figure out what are your different likely zones of material. So you want to kind of group certain measurements together based on their similarities, and then start by actually trying to identify all of the phases present for the whole system. So that can come both from sort of spot checks against samples as well as understanding of the mineralogy of that particular zone. And then you start to run your refinements in batch. And then once that's done, then you can actually go in and kind of quality check the goodness of the refinements and the potential for missed phases. So you kind of iterate that process. You try to find everything that you can, run refinements, and then you look for what's missing, find that, add it in, and then rerun things. So it's a bit of an iterative thing, but for small scale where we don't really know the system yet, it's a little bit more hands-on, whereas for more batch analysis, we can use the benefit of having lots of data to actually categorize things and catch different phases that we might be missing. Sebastian, just one thing, I think you missed a question a little bit further back, which was from
no, I think I answered it already. It
Oh,
was,
you did?
it was
Okay.
yeah, it was about in situ, and
Yeah, okay, I didn't
we
see your
don't
answer.
do
Okay.
in situ, but we are happy to make a connection to the ESRF or DZ if that is the case. So Monica is asking, is it possible to quantify only clay minerals by XRD by separating the fine fraction through
Decantation.
decantation? Oh, sorry.
To be honest, I don't know the answer to that question. I believe that there are probably cases where it is possible, and then there are probably other cases where it's not possible. So obviously, it also depends on like to what level do you want to identify all the clays? Like if you want to identify, certain clay systems, so you want to identify like kaolinite, and then you want to identify, kind of illite, smectite, and chlorite and stuff like that, and whether things are dioctahedral or trioctahedral. That's often possible even just directly. To do a better job, then there's different methods in terms of separating fine fractions, doing sort of oriented sample preparation and things like that. So we don't do those particular kind of measurements. And so it's certainly the case that if having extremely highly resolved differentiation of very similar clay phases is the most important thing to you, then you might need to do additional measurements to complement what we do to be able to discern those things. But yeah, we in many cases, I would imagine that if you do that, you can probably distinguish things quite well.
Brilliant. Next question. James is asking, can this technique quantify the mineral intensity, for example, clay content in a sample, and can it determine the clay crystalline? Oh God, to swim. I have problems today with English words. Crystalline.
Can this technique quantify the mineral intensity? I assume by mineral intensity you mean the mineral concentration. In that case, yeah, absolutely. So for some clay minerals, particularly more crystalline ones, so like kaolinite in some cases is coming in a very crystalline form. Different chlorites, for instance, can be very crystalline. Then in that case, we can model the clays in the same way that we do all of the other crystal phases with a crystal structure. Obviously, in many cases, you have smectites, illite smectites, and in these cases, you can have really disordered clay phases. And in those cases, sometimes you only can really observe the sort of stacking peak from the layers of the clay at very low angles, and it can be extremely broad. And then the rest of the signal is just contributing to the kind of slight variations and diffuse scattering under the curve. So in those cases, we can do a few different things. Sometimes they can still be modeled with a structure model. And then in other cases, we have actually
clay reference measurements. And we actually make sort of proxy models, which is a pattern that represents directly the measurement of the clay reference material. And then we have to develop a normalization factor for that phase contribution. And having the normalization factor allows us to calibrate the intensity against the phase concentration. And now I just lost the thing. Yeah, and in terms of determining the clay crystallinity, again, in some cases it can. So, I mean, from a general perspective, if you take that kind of 00L stacking peak at very low angle, you could broadly say that the peak width comes from crystallite size, is a type of measure of disorder of the system. Again, crystallite size is really coherent diffraction length. So you can use the width of that peak to say a domain size, essentially. Now, in reality, that's a bit trickier because clays have lots of stacking faults, and they can have other different types of interstratification defects similar to the layered double hydroxides that I showed. And so when you have all of these different kinds of defects present, while yes, the peak width is still sort of proportional to kind of coherent diffraction length, the domain size in the material, it gets a bit more convoluted in terms of like what that actually means for that phase. So you could have actually very large crystallites, very large particles of this material, but then the coherent scattering length in the material is only very small because of the buildup of defects. So it really depends on what you're trying to understand about the phase, and then really having kind of some context and sense of calibration for that. But yeah, in general, it's possible, but it may be more difficult in some cases than others.
Yeah. All right. So slide 40, I saw illitite and smectite in the minerals list. Did you develop a CIF file for this? Well, God's doing that's again a word I'm not going to try today.
Interstratificated.
Yeah. Or is there a database where to find this structure? So
yeah, that's right. There's not really like a good structure model for illite smectite. And so in the ICDD database, there is some DI list, which is d-spacings and relative intensities corresponding to measured data. So you can potentially use that to create what I'm saying is like a proxy model that you need then a calibration coefficient for. In our case, we have a sort of a library of clay reference materials that we've measured. And so we use that data to actually like encompass that signal in the refinement. But no, we did not develop a CIF file for it though.
All right. So if you have any more questions, please let us know. I also wanted to let you know, so we're happy to take a call to discuss your technical questions. Happy to take your call, book a call if you have a project where you think mineralogy on this scale could help you. We're also happy to partner with you if you are actually a consultant or a lab service where you think this is something that you want to offer to your clients. Happy to partner, happy to work with you to actually get this out there and create value for mining projects or other kind of material projects where synchrotron XRD is actually getting kind of like producing value for you and your clients. So yeah, with this, I think we're done with questions. Thanks a lot for attending. Thanks for all the questions. Happy to talk to you. I will be reaching out the next couple of days. Here is how much would this equipment typically cost? So James, we are a service, so you cannot buy the equipment. We are not on site. We only work as a mail-in service. So you would send us 5 to 10 grams of your sample. We would prepare it, we would measure it, and then you would get the results within for smaller batches, typical within 2 to 4 weeks. But there is no possibility to go with a synchrotron and install it on site or in a central facility. So, but super happy to work with you to provide this service. I hope this answers the question. Yeah, again, thanks a lot. Have a great, depending on where you are, rest of the day. I hope you enjoy the weekend, which will start very soon, and talk to you soon.